This video is on precipitation and neutralization reactions. So precipitate is a solid that forms when two solutions are mixed together. For example, if I have an aqueous solution of sodium carbonate mixed with an aqueous solution of magnesium nitrate, my products are magnesium carbonate and sodium nitrate. I need to look at my solubility rules to determine which, if either one of these, are precipitate. In other words, they become a solid when my two reactants are mixed together. If I look at the bottom of my page, my solubility rules are listed here. These are familiar, should be familiar to you, because they are similar to the solubility rules we used in chemistry. Most nitrates are soluble, and we care about carbonates. Most carbonates are only slightly soluble, except for those containing the cations in Rule 2, which were our alkali metals. So knowing that most nitrates are soluble, therefore my nitrate one is going to be soluble or aqueous, and my carbonate are only slightly soluble, so that means that'll stay a solid. So magnesium carbonate is a solid. That means that my magnesium carbonate would be my precipitate in my reaction. I can write something called a molecular equation, and my molecular equation is what I've written above. It's where I show my two reactants and my two products, listing their states of matter. Should also balance this equation by putting a 2 in front of my sodium nitrate. From here, I can better illustrate what this looks like in solution by completing a complete ionic equation. Here, strong electrolytes are represented as the separate ions they are in an aqueous solution. So, in our example here, that would look like this. My sodium carbonate is aqueous, so therefore I have sodium ions and carbonate ions. I have magnesium ions and nitrate ions. And I have 2 of those because of the 2 here, and 2 sodiums because of the 2 here. Okay, this is what a view of my reactants would actually look like. So I would, if I could see ions, I would see these floating around by themselves in my solution. After they're mixed, I would have my magnesium carbonate globs together to make my solid. But then my sodium nitrate doesn't actually come together like a compound. Instead, they're just, again, ions floating around in solution. And because of my coefficient 2 here, I have 2 of these and 2 of these. Thus, my reaction is balanced. Now, I have something called spectator ions, and spectator ions are my ions that don't form my solid. So my solid is formed by my magnesium and my carbonate ions, whereas my sodium and my nitrate ions are just hanging out watching things happen. So my spectator ions would be things that are the same, or ions that are the same on either side of my reaction. So that's my sodium, my nitrate, my sodium, and my nitrate. We can write a net ionic equation, and that's going to omit the spectator ions to actually show us what's really happening in our solution. So in a net ionic equation, we cancel out the things that are similar on both sides, so it'd be your sodium ions, your nitrate ions, sodium and nitrate, and that leaves us with our carbonate ion, our magnesium ion, and our solid precipitate magnesium carbonate. Notice that this is balanced as well. States are given. Another way that you can write this easily is by figuring out what is your solid made. So I'd write my magnesium carbonate, and which 2 ions did I need to make my magnesium carbonate? And that was my carbonate ion and my magnesium ion. It's good to note that it really does not matter where these two ions come from. A precipitate of magnesium carbonate can be made from many different aqueous solutions so long as the ions are present. So I could have something like any alkali metal, so I could have potassium carbonate, and I could have magnesium acetate as my two aqueous solutions, because all I care about is that I have a carbonate and a magnesium and that these are aqueous. Okay. So some summary steps for completing precipitation reactions, looking for net ionic or complete ionic equations and then net ionic equations, is to look at what would my products be, so it's that double replacement reaction. I have to know that my compounds must be electrically neutral, so my charges have to balance. And then I determine for my solubility rules to get a precipitate. These are also located on this page, page 148 of your textbook, but I copied and pasted them into here as well. So moving on to neutralization reactions. These are reactions between acids and bases. So there are two different definitions of acids and bases that we're going to use. There's the Arrhenius definition, which tells us that an acid will release hydrogen ions in solution, where a base will release hydroxide ions in solution. And then there's the Bronsted-Lowry definition, which talks about being proton donors and acceptors, and a proton is just a hydrogen ion. Okay, so to note that a proton is the same as a hydrogen ion, because all a hydrogen ion is just a proton. There's no electron or neutron. So a Bronsted-Lowry acid is a proton donor, and then a Bronsted-Lowry base is a proton acceptor. And we're going to look at what that means here in a second. So if I am looking at the reaction between two strong electrolytes, so that's a strong base and a strong acid. So sodium hydroxide is a strong base, and hydrochloric acid is a strong acid. They're going to react together into a double replacement reaction, where I'm going to have sodium chloride and I'm going to have water. I can write water as HOH or H2O, doesn't matter. A lot of times if you have an acid-base reaction, it's helpful to write it as HOH because it's easier to balance. So I have my reaction here. I'll notice that for this to happen, my hydrogen from my hydrochloric acid bumps off my sodium. So my hydrochloric acid released that hydrogen ion in solution, and that hydrogen ion in solution paired up with my hydroxide. So water is a liquid, sodium chloride is aqueous. So if I were first to write my complete ionic reaction, I'd have sodium ions, hydroxide ions, hydrogen ions, chloride ions to make sodium ions, chloride ions, and H2O. Being a liquid, it doesn't get split up into its ions. Crossing off like things on either side, sodium and sodium, chlorine and chlorine, my net ionic equation is my OH plus my H plus makes HOH, liquid. And these are both aqueous. Okay. So we can see that my strong electrolytes are going to react. Hydrogen gets donated to the hydroxide, and these fully dissociate into their ions in solution. If I have one strong electrolyte and one weak electrolyte and they react, well, my weak electrolyte here is my acetic acid. This means that it will not fully dissociate. So when that breaks apart into solution, this doesn't break apart. Looking at my double replacement reaction, my hydrogen is going to swap out with my potassium. So I have HOH which is my liquid water, and then potassium acetate, which is aqueous. My acetic acid is a proton donor and will give hydrogen ions to the hydroxide. Okay. So if I draw this out, that again is my potassium ions, my hydroxide ions, because that fully dissociates, with my non-fully dissociating weak acid to make my water and my ions in solution because this does dissociate. So crossing off like terms on either side, my potassium comes off on either side, and I'm left with everything else. So my net ionic here is my OH plus my acetic acid makes my water and my acetate ions. So for any hydroxide, because it's such a strong base, we are going to use for stoichiometry purposes, that it reacts completely with the weak acids. So that means it fully dissociates and reacts, bopping off that hydrogen to make the anion an ion in solution for the acid. Looking at Bronsted-Lowry acids and bases, they're going to react the same way. We're just looking for protons now instead of hydrogen ions. So here, same thing. I have HOH, my water, and sodium chloride. And my net ionic is the same as before. Because now I'm saying this proton donor of my hydrogen to my hydroxide, that's what creates this as an acid. The same thing happens during my weak electrolyte with my strong base. Here, acetic acid is a proton donor, like we saw above. I make my water, and then I also make my potassium acetate. My acetic acid being this weak electrolyte, the acetic acid is going to donate a proton to my OH. So just like before, my acetic acid goes and donates that proton. So potassium hydroxide fully dissociates into my hydroxide ions. I still have my acetic acid, which is not really dissociating here, but it is going to give up this hydrogen to the hydroxide to make my water, and then it leaves itself with its ion floating around in solution. So again, hydroxide is such a strong base that in stoichiometry we assume that it reacts completely with any weak acid, no matter if we're looking at the Bronsted-Lowry definition or the Arrhenius definition. So now let's look at some stoichiometry solution calculations. We're going to do this reaction in class, but to look at it ahead of time, I want to know the mass of lead to iodide formed when 20 milliliters of 0.5 molar lead to nitrate and 25 milliliters of 0.75 molar potassium iodide are mixed. So my reaction is between my lead to nitrate, which is aqueous, and my potassium iodide, which is also aqueous, are going to form potassium nitrate. I know all nitrates are aqueous, and lead 2 iodide, which if you remember back from chemistry, that's that yellow precipitate that you made in your limiting reactant lab. So if we go back to our solubility rules, we can see that for iodines, they are soluble except with lead. So iodide salts are soluble except when they're mixed with lead 2, which is what we have. So that's our solid. Okay. The first thing we want to compare is determine the moles of each ion that's present. So instead of doing 2 very long limiting reactant stoichiometry calculations, we can compare the molar ratio of what's required in our product of the lead 2 iodide. So we're first going to calculate how many moles of each reactant we have of our 20 milliliters of our lead nitrate and our 25 milliliters of our potassium iodide. So converting milliliters to liters, I have 0.020 liters of lead 2 nitrate, which, using my molarity as my conversion factor, I have 0.5 moles per 1 liter. Which gives me 0.01 moles of PbNO3(2), or my moles of lead that I want to know about. And then I have 0.025 liters of potassium iodide. And using my molarity of my 0.75, I have 0.75 moles of Ki per every 1 liter of Ki. And that gives me 0.01875 moles of Ki, which tells me my moles of iodine. If I look at my ratio of Pbi plus 2 ions to I2 ions in Pbi2, my ratio of Pb plus 2 to I negative in Pbi2, we can see my ratio is 1 lead ion to 2 iodide ions. Given to me above, for my calculation, I see that I have 0.01 moles of lead to 0.01875 moles of iodide. So I need this ratio to be 1 to 2, and right now it's 1 to a little less than 2. So that means that my limiting reactant must be here. My I is my limiting reactant. So to determine how much I'm actually going to have, I take my limiting reactant amount and I can convert that into my mass of product using stoichiometry. And then I get 4.3 grams PbI2 can actually be made. So this is kind of a nice shortcut to use your mole ratios to help you identify limiting reactants quicker than we've done before. And then you just have a smaller conversion from moles to grams of the product that you want. Let's do another equation example with neutralization. So here we have a strong acid and a strong base. and we're going to figure out what volume of hydrochloric acid is required to neutralize 40 milliliters of 1.2 molar sodium hydroxide. So we start with what we're given, which is our known amounts here. So I have 40.0 milliliters, which is 0.040 liters of sodium hydroxide. And this one is just all stoichiometry. So my first conversion to get from liters to moles, I use my molarity, which has the units of 1 liter per 1.2 moles of sodium hydroxide. I can go from moles of sodium hydroxide to moles of hydrochloric acid looking at my balanced equation. So when I write that, that's sodium hydroxide plus hydrochloric acid makes sodium chloride and water, which is a 1:1:1:1 ratio. And then I can go from moles of hydrochloric acid to liters to find volume because I have my molar mass. So for every 0.80 moles of HCl in 1 liter, multiply across the top, divide by the bottom, and I get 0.06 liters, which is kind of hard to wrap your head around. So that's 60 milliliters of your 0.8 molar hydrochloric acid. So again, on these, start with what you're given, this whole amount that you know something about, and use that to find out and convert to the thing that you don't know much about. To do neutralizations in the lab, we'll use something called a titration. And a titration setup looks like this. A titration is a volumetric analysis where one solution is used to analyze another. The titrant is the solution of known concentration, which we find in the burette. And this thing here is your burette. The analyte is the solution of unknown concentration, which we can find in the E-flask or Erlenmeyer flask. And think of that you're going to analyze. Thanks, Days. You're going to analyze the analyte. The indicator is the substance that changes color at the endpoint, which we'll put in the analyte because that's what we care about when it changes pH. And then the equivalence point is when enough titrant has been added to completely react with the unknown solution. And it's important for us to have the endpoint equal to the equivalence point. So the endpoint being where we get neutralization to happen and where our indicator changes color, we want that to be at the same place. So it changes color when we want it to. And then we know we can stop adding our titrant into our analyte.